Okay, it says we're recording now. So let me share my screen here. All right, so we're going to talk about probability. So the funny thing I have to say is whenever we start talking about statistics, a lot of times people will say, hey, especially guys, they'll be like, hey, can you help me with my fantasy football or something like that. So every statistician needs to know a little bit about statistics, but the idea here is, as we talk about, I'm much better at probability than I am, or excuse me, I'm much better at statistics than I am at probability, but everybody needs to know some simple probability. So the idea here is probability we use to try to predict an outcome. So Blaise Pascal was one of the first mathematicians to figure out the probability of winning, and it was because a bunch of gamblers came to him and they were like, hey, we think we should be making more money than we are. Can you tell us what we're doing wrong? And so so the idea with probability is it's a number between 0 and 1 that describes the proportion of times an outcome occurs. So there are different ways to figure out probability. There are the theoretical, empirical, and personal. Now, personal is always the fun one to do. In fact, let me ask you guys. Bridger, by the way, can you hear me, Bridger? Bridger should send me an email and say why he can't answer. Because I don't know if you can hear and you're just walking away or what. But so Easton, we'll pick on you first. Do you have a favorite team?
Not really.
No? You're not a sports guy at all?
No, not really.
Oh, what is wrong with you? Seth, how about you? Do you have a favorite team?
What sport was it? Sorry.
You pick the sport. I don't care. Who's your team?
Let's go 49ers.
49ers. Okay, so what's the probability that the 49ers win the Super Bowl if we have a season this year? Or maybe I should ask that question. What's the probability we have a football season this year?
It's not looking very high.
Solid, very high. Give me a number between 0 and 1.
0.2.
0.2, so 20%? So you think we're not going to have a season?
I don't know. I have no clue.
All right, let me ask you, Wes. What do you think? Are we going to have a football season this year?
I think so.
What's the probability we have a season?
Probably about 78%.
78%. Wow, that was precise. Okay, Janie, are you a football fan?
I watch the games and I act like I know what's going on.
You
so
act
that's
like
considered a fan.
Okay, so what's the probability we're going to have a football season this year?
I would give it like a 50%.
50%. Okay. So Janie, Seth, and Wes, how did you come up with your numbers? I didn't hear you, Seth. I just heard a buzz.
Oh, I don't know. I just said whatever.
You just made it up, right?
Yeah.
Okay. That's the perfect answer. That's exactly what a personal probability is. It's a personal opinion on how something likely will happen. It doesn't have to be based on any facts, but only your personal intuition. So you can think of Super Bowl odds posted next year. That would be an example of a personal probability. Okay? Now, let's talk about the other two. We're not going to talk about that very much other than the fact that those are the ones that most people are familiar with. Theoretical, we're going to try to calculate something based on rules, okay? And so let me ask you guys another question. Let's pick on somebody else here. How about, we're going to go back to Easton since he chickened out on the football question. So Easton, what is the probability that if I flip a coin, it comes up heads?
Just the one time?
Just one time.
About 50%.
50%. How did you come up with that?
Because there's two sides to the coin, and so
Two
it's
sides.
going to land on one or the other.
One or the other. And so 1 out of 2, that would be 50%. Okay. So that was based on a rule. That wasn't just making it up like Seth did, right? Okay. Allie, do you ever play cards?
Yes.
Okay. So you know the rules for cards. So what's the probability if we were playing cards that I pulled a king out of a deck of cards? Do you know?
So there's 52 cards and only like 4 kings. So whatever 4 over 32 is.
4 over 52.
Oh, 52. I'm sorry.
She's a bad card player. She only thinks there's 32 cards. Okay, but yes. So once again, you figured out the probability, and I'm impressed because sometimes when I ask this question, people are like, I don't know, I don't play cards. But you did a theoretical because it was based on rules. And in fact, I like how you said that. There's 52 cards, there's 4 kings, so it's got to be 4 out of 52. Okay, so that's the example of a theoretical probability. So we'll be doing a lot of that in this class. Now, empirical, we measure how often something happens. Now, I'm going to ask a terrible question. Elise, you're the next one. No, Allie. Well, one of you two. You guys can fight over it. I'll let you pick. Okay? Now, you're both women. So let me ask you this terrible question. What is the probability that either one of you get breast cancer?
50%.
50%? How did you come up with that?
Because it's just the two of us.
Oh, there's 2 of you. Oh, you're assuming that one of the 2 is going to get it?
Yeah.
I don't think it's that high, is it?
Well, it kind of depends on like genetics and like past history, if it like runs in your family condition. So I don't know exactly what that probability.
Okay, and I don't know what the probability is either, but I'm sure it's lower than 50%, thank heaven. We don't want either one of you getting breast cancer. But how, if you are the scientist in charge of figuring out how the probability that a woman, any woman, okay, so we're basing it not out of 2 people, we're basing it out of, you know, the millions of people in the United States. How would we figure out, or how would you figure out the probability that a woman would get breast cancer?
Well, I guess you would have to, if you could take a census, but probably not, take a sample size or to try and figure out exactly how many women as of now out of the population have breast cancer, and then kind of figure it out from there.
Exactly correct. That's exactly right. So essentially what they do for breast cancer, and I could have asked it for prostate cancer too, but actually, Manuel, I'll ask you. So this is Wes, Seth, Easton, and Bridger, if he can hear me. What's the probability that you guys are going to get prostate cancer? Do you guys know?
Hopefully it's not that high.
Yeah, it's actually close to 100%, believe it or not.
Yeah, once you get over the age of like 75, correct?
Yeah, if something else doesn't kill you first, almost every man is going to get prostate cancer. It's a terrible thing. So it's worse than breast cancer. Almost every man will get prostate cancer if they don't die from something else first. So it's terrible. So anyway, the idea here is that I'm trying to bring up, not to talk about cancer, is empirical, just like Ali said. We measure how often something happens. That is an empirical. So the two that we're going to talk mostly about in here are empirical and theoretical. We won't talk very much about personal, but all right. So let's do some quick and easy, hopefully easy math. So this is an empirical model. They went through the census and they figured out the probability that a woman aged 25 to 29 years old is married. And so they figured the never marrieds were 0.503, the marrieds were 0.452, the widoweds were 0.003, and the divorced was 0.042. So, whoops, didn't mean to do that. So what is the probability that a woman is not married according to the table? So I should pick on a woman for this. Let's see. How about Elise? We'll go back to you since Ali got the empirical one. How would you calculate the probability that a woman was not married according to this table?
So I think we're gonna do 0.503 divided by the sum of all these numbers.
Divide?
Yeah. Yes.
Okay, so no, that's not quite right.
No, never mind. It should be 0.503.
Okay, so now remember here, so this is a never married, but if a person is married, they could be widowed or they is not married. They could be widowed or divorced too, right?
So never married, widow, or divorced.
So they could be never married,
Okay.
or they could be the probability that they are widowed, and we could add together the probability that a woman is divorced, right?
Yes.
Okay, and so I probably shouldn't have told you that, but you can simply add them. Now, we're making an assumption here, right?
Okay. So we are adding 0.503, 0.003, and 0.042.
That's correct. So you can add them together, but what's the assumption that we're making? A woman that's 25 to 29, could they be in more than one category at a time? Could a 29-year-old woman be widowed, divorced, and married?
Potentially, yes.
Potentially, yes. Okay. They couldn't be never married and married at the same time, but yeah. So we're making an assumption that you can only be in one category. In one category. Okay. And so so that's one way that we could do it. Okay. And I believe that in this case, the answer, I don't know, I can't remember, but I think it's well, we'll do that. We'll figure out that answer in just a minute. Now, is there another way to do this problem? We'll go to Wes. Wes, can you think of any other possible ways to get the right answer on this?
You could probably you could probably just go ahead and subtract the married people from 1.
Very good. All right. So you said if we took 1 minus the probability that a woman is married, that would be the correct answer also. So in that case, we would go 1 minus 0.0452, which equals 0.548. And I think this one also equals 0.548. Okay? So there are two ways to do this. Now this is called the complement rule. And that is with an E, not with an I. I'm not complimenting you on doing your good math, although I did compliment Wes on coming up with that, so that was good. But the complement rule, okay? And so one of the things that you'll find is sometimes the complement rule is easier way to figure out probability than adding them up, just like we did there, okay? So let's talk a little bit about probability rules, okay? So the rules are any probability must be between 0 and 1. So I always like to joke with my math people or my football fans that, you know, the Cleveland Browns have been terrible for a long time. And I say, what's the probability they win the Super Bowl? And you can't say that it's negative, even though you may want to. It's always got to be between 0 and 1. You could say 0, probability might be 0, but it's not negative. You also can't say, actually, Seth, I never got, who was your favorite? Oh, it was the 49ers, right? You're a 49er fan?
Yeah.
So you can't say that the probability will be 110% because even it's got to be less than 100%, okay? In fact, you can think of these as percentages as well, okay? So rule number 2, all the probabilities must add to 1 if independent. Now that's also a big assumption here. So if we went back up to our model here, and if we added all 4 of those categories, they would add up to 1. Okay. The probability that an event does not occur is 1 minus the probability of the event, and that's what Wes just showed us with the complement rule. And if 2 events have no outcomes in common, then you can add the probabilities. So another example would be like the coin flip. You got two options, and it's either a head or a tail. You can't get a head and a tail at the same time, and so therefore you can add the probabilities. And also going back to here, we're assuming that a woman can only be in one category at a time. Okay, while it's possible that a woman could be both widowed, divorced, and never married, we're assuming that she has to be in only one category when we're adding these together. She can't be in more than one. Okay. All right, so next thing we're going to talk about is the sample space. Okay. So sample space is very useful in theoretical models. And so one of the things we do is we try to figure out all the possible outcomes. And this can be especially helpful in rolling 2 dice. Okay, so does anybody know right off the top of their head? We're going to find out what kind of good gamblers you are. Do you know what's the probability of rolling a 5 on dice? Does anybody know that off the top of their head? Because we're going to figure it out.
1 out of 6.
1 out of 6? Okay, so that was a good guess. But we're rolling 2 dice, not just 1.
These are just 6-sided dice?
Yeah, these are 6-sided dice, but we're rolling 2 dice. So was that Seth that answered that? That would be correct if you were rolling 1 dice.
Yeah, I thought it was just 1.
Yeah, it's 2 dice. Okay. So now here's the deal. Anybody else want to take a stab before we give you the right answer?
Wouldn't it be the probability of rolling all the different combinations that add up to 5 with the 2 different dice?
Do you know what that value is off the top of your head?
No.
No. But you're on the right track, Easton, okay? So here's what we're going to do is we're going to write out the sample space. Okay. Now, one of my favorite things to do on the test is to do dice problems. because people are lazy and they don't like to do this. Okay, and then they will say, I just want to get the problem wrong, and so I'm not going to do this the hard way. Okay, now this isn't hard. It's a little bit time consuming though. Okay, so just as Easton said, we're going to write out all the possible combinations. So you could get a 1 and a 1, or you could get a 1 and a 2, 1 3, 1 4, 1 5, 1 6. Or you could get a 2 1, 2 2, 2 3, 2 4, 2 5, 2 6. And we'll just keep going. Now, one thing that people will say, as you can see, I'm writing these out, and I don't know if this is a good idea to type and write at the same time, but we'll see how good I do. Some people will say, well, here, let me finish this before I mess this up. I did talk and type at the same time. Okay, so we've got all of the possibilities of rolling 2 dice. Now, some of you may say, oh, it doesn't matter. Why did you so I listed about with assuming that the order matters. Okay. Now, as we look at this, I could get a 4 and a 1. I could get a 3 and a 2. I could get a 2 and a 3. I could get a 1 and a 4. Okay, so those are the only ways that I can roll a 5, right? Okay. So how many do I have highlighted?
4.
I've got 4, and how many total options are there?
36.
36. So you could say that the correct answer would be 4 out of 36, or if you wanted to simplify us to 1 out of 9, that would work as well. Okay. Now, let's see here if, let's pretend that I said, well, order doesn't matter, and I don't want to write out all these because I'm lazy. Okay. So we could probably go ahead and get rid of all these numbers here because these are duplicates, right? Probably keep that one there. Okay, so if I only wanted to write out half of these, okay, so I just deleted half of them. I've only got 2 highlighted now, right? But the question is, how many do I have? Now, one of the nice things about Excel is it will count for me. So if I highlight all these things, because I don't want to count, but you can see down here, I've got 21. So is 2 out of 21 the same thing as 4 out of 36 or 1 out of 9? No. Okay, so what I'm going to tell you is there are some cases, 1 out of 9 works out to be about 11%, whereas 2 out of 21 works out to be 9.5%. Okay, so they're similar, right? Okay, but the problem is this is kind of the gambler's fallacy here that we were talking about at the beginning. If a gambler says, oh, order doesn't matter, and I think something's supposed to happen only 9.5% of the time, and it in reality happens 11% of the time, then you're going to lose out on some money, right? Especially if you want to cheat and win, okay? So, always assume that order matters, okay? And so writing out the sample space is very, very useful, okay? Now, another thing that I could ask, I don't want to retype it, I'm going to do this. Okay. All right, so I've got it back here. What if I said find the probability that of rolling a 8 or greater. Okay, how would you do that?
Find all the possibilities, add up to 8, and then subtract, or what's it called, by the total.
Yeah.
Yeah.
You're on the right track. Okay. So 8. So 6 and 2 is 8. So all of these are greater than 8, right? So we'll pick a different color, like blue. Okay. So all of those are 8 or greater. All of these here are 8 or greater. These are 8s, 8, and 8. Okay. So now I just have to count, right? So this column works out to be 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Okay. So what's the probability of rolling an 8 or greater?
(15/36).
15 out of 36. Now, do you see how easy that was when you have your sample space? Could you have done that without a sample space?
Maybe with a lot of work.
Maybe with a lot of work, but see, it was really easy, right? Now, I have a feeling, a strong feeling, that I'm going to give you some dice problems on the test. And we're going to find out who wants to get it right and who wants to get it wrong. Okay? And I'm totally fine if you want to leave it at 15 out of 36. I guess if you wanted to simplify that, those are both divisible by 3, so that would be 5 out of 12. That would be the same answer. But sometimes it's easier just to leave it in out of 36 than to simplify the fraction, so I'm fine with that. Okay? All right, so let me do, oh, I did the same thing twice there. Okay, so we've done a bunch of those. Now, the idea here is one of the things that we can do with this is we can come up with a sampling distribution or density curve. And this is the values of repeated samples and how often it takes those values. Often these can be simulated with a normal curve. And so let's do another example. Okay, so this was a dice problem. Okay, now here's another one. This one's going to be a heads and tails. Okay. So here's what I want to do on this one. Okay, so what if I told you to write out the sample space, or the number of heads out of 3 tosses of a coin? Okay. So whose turn is it now? I think it must be Janie's turn. Janie, what are all the possible combinations of heads and tails if you flip a coin 3 times?
I feel like this is a super easy answer, but it's like not clicking in my head. Because
Okay.
if we flipped it 2 times, it's 50%. So if we did it 3, wouldn't it be like 25%?
Well, that's a good question, but the problem is, let me just say here, probability can be very tricky, and so that's where sample space comes in. And so before we start figuring out numbers, let's figure out possibilities. Okay. So what's the probability I get a head on the first try? Or not the probability. Here, let's do it this way. I could get a head on the first one, a head on the second one, and a head on the third one. Correct?
Yeah.
Okay. Now let's draw out the list of all the possibilities. Okay, so if I could get 3 heads in a row, right? What's another possibility I could get?
It could be like, you know, heads, tail.
Tails. Okay, what else?
Could be tails.
Tail. Are there any others?
Could be heads, tails.
Heads, tails. Okay.
Or heads, tails, heads.
Okay.
I think that's it.
Yeah, there's actually more than that.
Oh,
and I like to do them in, remember, we said earlier here that always assume that order matters. So the easiest thing to do, if we start with 3 heads, and then we went head, tail. So let's just move that tail around. So I could have a head, tail, head, or I could have a tail, head, right? So there's 3 ways to get a tail. One tail. Correct?
Yeah.
Okay, so now we've got 2 tails. So I don't need that one again because I've already listed it. But now the idea here is we can move the head around. So I could have a head first and then 2 tails, or I could have a tail, head, tail, or I could have tail, tail, head. And then I could have tail, 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 right? Okay. Now that we've gotten all of these out, okay, I could list out the probability of 1 head, or the probability of 2 heads, or the probability of 3 heads, or the probability, well, that's it. Actually, there's one more probability. We could get no heads, right? 0 heads. Okay. Now, it may be tempting to say here, oh, well, there's only 4 possibilities, right? And there are 4 possibilities when you don't think about the order. Okay. But when you're thinking about the order here, okay, we've got 8 possibilities rather than just these 4. Okay. So there's 2 ways to think about writing out the sample space. Sample space is to list out what happens in every order here. And then we could also just say, well, okay, what's the probability of 0 heads? Okay, so the probability of 0 heads in here is what?
One out of 8.
So we could do 1 out of 8. Okay. Now, probability of 1 head. What's the probability of 1 head?
It'd be 4 out of 8.
No, just 3 out of 8. That makes sense? What's the probability of 2 heads? You got 2 heads in all of those. Yep, 3 out of 8. 3 out of 8. Probability of 3 heads.
1 out of 8.
1 out of 8. Okay. So it was really a good idea that I listed out all 8 of my sample sizes here. Okay. So here's the thing. Now what we can do with this here information here is you can think of these as your probabilities. Now, before we did this, you might say, oh, well, I've only got 4 options, so each one is 1/4. Can you see that's bad math? That's gambler's math. Okay? That's why they were getting this stuff wrong, is because they assumed that order didn't matter. Okay? And in a way, it's true, the order doesn't matter. Any one of these is 1 out of 8, but when you start combining things in here, you can see there's 3 ways to get 1 or 2 heads, and there's 3 ways to get 1 head. There's only 1 way to get no heads or 3 heads. Okay, so these are not all equally likely. And so if I wanted to convert these to a decimal here, 3 out of 8, 3 out of 8, and 1 out of 8. Okay. So we could also think of these as probabilities. Now, do you guys remember how to make a histogram? That was on the last test. That was like so long ago. That was like a week ago.
I had a hard time doing my homework this morning. That was just 2 days ago.
Okay. Anybody remember how to do that?
Yeah.
How do you do that, Seth?
So you'd put like the probability. You could do that on the bottom, and I guess like the percentage probability on the bottom. And do like 0.1, 0.2, 0.3.
Okay. So you put both things on the bottom, but you don't want to put both things on the bottom.
I was saying just the.
So we could do the number of heads here.
Okay, I put it backwards then.
Okay. And then we could do the probability here. Okay. And then, just as you said, so if we did 0.1, 0.2, 0.3, 0.4. Okay. So 0.4. Why is everything underlined? 0.4, 0.3, 0.2, 0.1. Sorry, my scale's not very good, but that's close enough. Okay. So then what would I put along the bottom then? So if I've got number of heads here.
The probability of 0.
0 heads.
Then 1, 2, 3.
2. And one of the things that people always forget is the 0. But there is a probability of 0 heads in this case. Okay. 3. All right, that's good enough. We don't need 4 heads when we're only flipping it 3 times. Okay. All right, so then, in this case, what do you do next?
With 0, you put 1 point up to 1.25.
Okay, so we'll draw a box right here.
Yeah, and they're all connected. 1 point.
So 0.375 would probably be about right here. Boxes should all touch.
0.75, yeah, all boxes touch.
Oops, that should be the same size though. Hopefully the same width. And then once again, 3 heads, which would be about right there. Okay. So you've already forgotten how to make a histogram, and that was just on the last test. Okay. So this is, give it a title. So title such as probability in 3 coin flips. Okay. So you can do that on paper when we're doing this next on the test on Friday. Remember, there's a test on Friday, and it's going to be right after class, like we did last time. Or, well, we're only going to meet for an hour, and then you guys can do the test. Okay? Are you all going to take it on time? Okay, I got
Yes.
a nod. All right. Okay. All right. So yeah. So we'll do a review the first hour, and then so 9 o'clock the test will open, and then you'll have. I'm going to give you 90 minutes again. Okay. And if I ask you to draw a histogram, you'll just draw that on paper. Okay. All right. Piece of cake. I have a feeling we're going to get done early today. Let's do a review today. Let's see here. Okay, so the idea here, what we've done is we've created a sampling distribution or a density curve. Now, would you say that that's normally distributed?
Yes.
Yeah, roughly. They won't always be, but yeah, that looks probably pretty roughly symmetric or normal. Okay. Not every curve will be normally distributed. Okay. Now I talk a little bit about a binomial distribution, and we can talk a little bit about that. So the idea with a binomial distribution is you only have two options. Okay, so a coin flip would be one, but it doesn't always have to be 50-50. Okay, I'm trying to remember. I don't think I have. Oh, I copied a lot of my information in here twice. In fact, okay, we'll do some more here in a minute, but so an example is a survey. Normally I make you guys go out and do a survey, but I'm not doing that this semester. You guys are lucky. So, you know, we could do a survey, for example, with who do you want for president, Joe Biden or Donald Trump? And you could ask people, but the idea here is we're only going to have two options. It gets really complicated if you have more than two. And some people might say, well, I don't like either one of them. I'm either not going to vote or I think I just heard that Justin Amash, or I don't know if that was an old thing, is running for president. And so we're assuming that in this case, if we want to keep the math easy, we're going to be like, no, you can only vote for one of these two. And some people may say, well, I don't like either one of them. I'm going to vote for third party, which you could do, but it just makes the math a lot harder. So we're just saying, just limit your options to two, and that will make the math easy. So we'll probably have time at the end of the class that I might do something, but let's keep going here with another example. I should have picked somebody in the class, but here's the example. Sophia has 3 tickets to a concert. She wants to take 2 friends, but of course 4 want to go. Yolanda, Michael, Marissa, except for, you know what, we're not going to put the same name in here. We're going to pick Elise in here. Yolanda, Michael, Elise, and Kevin. Okay. So what would be the sample space for the 2 friends that could go? Here's what I'm going to do. I'm going to copy this. And we're going to, because I think it's easier if I do it here. Okay. Oh, actually, I should copy this. I'm going to update my notes and we'll put this in here. All right. Okay. So what would be the sample space? Sophia has 3 tickets. She wants to take 2 friends. Of course, Sophia is going. So we're only going to worry about the 2 friends that want to go. So what are all the possibilities that we could do in this?
So wouldn't you you would assume that order matters, and so you'd pick one of the friends to start with, and then do that friend plus each of the other ones one time.
You want to take it away, Michael or Easton?
Sure.
We don't even have a Michael in the class.
So if we say Yolanda's for the first bit, Yolanda's for sure going, so it'd be Yolanda and Michael, or Yolanda and Elise, or Yolanda and Kevin.
Okay.
And then you would assume that Michael's going. Would you redo Michael and Yolanda? Yeah, because order matters. Yeah,
because we're going to assume that order matters, right? Because we want to get it right.
And then
we don't want to be like a gambler that messes it up.
And you do Michael and Elise, and then Michael and Kevin.
Okay.
And then you do Elise and Yolanda, Elise and Michael, and Elise and Kevin. And then you do Kevin and Yolanda, Kevin and Michael, Kevin and Elise.
Okay. So well done. Okay. So that was perfect. Can you do this on a test?
I hope so.
Okay. What is the probability that she takes 2 guys? Sophia takes 2 guys. She would probably like that, wouldn't she? If she was single, at least. So since Easton answered that, we got to have somebody else answer. What do you think, Janie?
It's 2 out of 3, right?
2 out of 3?
Yeah.
Okay, well, we've got this nice sample space that you've conveniently ignored.
Wait, because there's Michael and Kevin, and then
Michael and Kevin. Okay, that's 1.
Yeah. And then we have Kevin and Michael.
Kevin and Michael.
And then aren't the rest all girls?
Yeah. So what do we got?
So
if we count all the number of options, we've got 12 options, right? 12 options.
Yeah. So it'd be like 2 out of 12.
So that would be 2 out of 12, or you could say 1 out of 6. Okay. How about this one? What is the probability that she goes with, that Elise goes? We're going to have to ask Elise here because Elise, if there was a concert, who would you want to go to? Let's see. You're still here. I was scared you ditched us. Who would you like to go see in concert, Elise?
Who do I want to choose?
Yeah.
Do you want me to give you the answer or to choose someone?
Which concert do you want to go to? You don't sound like a country music fan to me. Am I right?
Yeah.
Do you have a favorite group or anything?
Not really.
Not really. So you
Yes.
don't care about this concert. Who cares? All right. Well, you're good friends with Sophia, at least according to this problem. So what's the probability you're going to this concert you don't care about?
So I think. So I'm gonna pick up Yolanda and Alice.
So Yolanda and Elise.
Yes.
Pick orange. Okay.
Yes.
What else?
And I don't know what name that is, but it's M.A.
Michael and Elise.
Yes. And Alice and Calvin.
Elise and Kevin. Okay.
And Alice and Yolanda.
Okay.
And Calvin and Alice.
Kevin and Elise, I think you missed one.
And Alice and M.
Michael.
Michael, yeah.
Yeah, you just don't like Michael, do you? No, just kidding. Okay, so you just have to highlight all the A's. So how many A's do we have there? You just got to count them.
So 1, 2, 3, 4, 5, 6. That's 6.
Okay.
Yes.
6 out of how many possibilities?
12.
12. Okay. Do you see how, which ends up being about 1/2, right? It's like flipping a coin.
Yes.
Okay. All right. So see how easy this is once you have your sample space?
Yes.
Are you going to write out your sample space, or are you going to be lazy on the tests?
I'm gonna write the sample space.
All right. Cool. Yeah. Even on the dice problem? I can almost guarantee I'm going to give you guys a dice problem just because I want to see who's lazy and will do it and won't do it. Okay? All right. So is there anything else here? Oh, you know what? Well, let's see. Could you make a probability distribution by gender? Would you guys feel comfortable doing that?
Well, gender, there's only 2 categories, right? So would it just be?
Yeah, but you could have 2 guys or 1 guy. In fact, yeah, what would be the if we do the number of men, if that's what count, or do you want to do number of women? I don't care. We'll count the women. Number of women who attend. What are all the possibilities?
Are we just counting the friends, or are we counting Sophia as well?
We're ignoring Sophia. Yeah, just
Okay.
the friends.
So you'd have a probability that 0 women go. The 1 woman goes, or 2 women go.
2 women go. Okay. Probability that 0 women go.
That's 1 out of 6, isn't it?
Yeah. Yeah, because we did that before, right? That was Kevin and Mike and Kevin. Okay. So that was 2 out of 12. Probability that 1 man goes. Actually, we didn't figure that one out, did we? 1 man and 1 woman. We're going to have to get rid of all our color codes in here now.
Wouldn't it be 8/12?
So would it be? Well, actually, we could probably figure that out. We'll ignore that one for a minute. We're going to find out if Wes is correct. 2 women would also be 2 out of 12, right?
And that's how I figured it out that way.
So you did it that way. So that's 4 out of 12. And so then this one would have to be 8 out of 12, right?
Correct.
Okay, so you use the complement rule. See how easy that is? Complement rule. So I'm going to compliment you on using the complement rule.
I appreciate it.
All right. So, and of course, it's probably easier to use these as percentages. 2 out of 12. 8 out of 12. And 2 out of 12. Okay. So could you make a probability histogram?
I could, now that Seth reminded us how to do it.
Okay. How about you, Allie? Could you do it?
Yeah, I could do it.
Okay, cool. All right. So remember histograms. We're gonna not forget them. Okay. So they'll be on the test. All right. What else do I want to talk about? Okay. So I asked a bunch of questions there. Myth of randomness. Okay. So let's talk about. So this is a concert here that Elise doesn't want to go to because she doesn't have a favorite group. How can you say that, Elise? All right. So this we're going to talk about the myth of randomness. Okay. So if I had tail, 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 head, 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 I flipped a coin 6 times and I got tail, tail, head. And then the second time I flipped it, I got head, tail, head, head, tail, tail. Okay. So who says that option 1, oh, this is where I really wish I could raise hands. Who says that option 1 is more random? Or we're going to ask everybody. Elise, is option 1 more random? Which one's more random, 1 or 2?
It's 2.
2? Okay, so Elise is going with 2. How about you, Allie?
Well, they both have like a 50% chance of, so would one of them be more random than the other one?
Well, that's what I'm asking you.
I personally don't think so.
You can't
but I guess
ask me when I ask you.
Well, I don't think that, I think that they're both like random because of the 50-50 thing. But like if out of like order, that's like most mixed up, it's number 2.
Okay. So, okay, well, I'm going to let that go. Easton, what do you think?
I'm going to say number 1 is more random.
You're going to say 1 is more random. How about Janie?
I'm going to say 2 is more random.
2 is more random. Seth?
I think they're both equally as random.
They're equally random. Oh, Seth's breaking the rules here. Okay. How about Wes?
I'm with Allie and Seth. I mean, they both have the same probability of occurring.
That is correct. They are equally random. That was a trick question, wasn't it? I shouldn't do that. Okay. The problem is that we see patterns. You can see a pattern here, right? And so you say, oh, that's therefore this one, most people would say this one is more random. But as half the class said, they're actually equally random. Okay. And because, well, this just kind of goes to show that humans are really bad at probability. Okay. So the fact that each outcome is equally likely, if you would have done a sample space thing, you would have seen that. You're going to see runs of heads and tails over time. it's still going to be random. Okay. Now there's a fun thing. There's a fun video that I like to show, but the problem is you can't hear it. I wish that you guys could hear, but here, I'll just do it this way. Mythbusters toast. Butter side up, that's the one. So if you guys want to watch this after class or something, we'll just watch it because obviously you guys can't hear it. In fact, I'm going to turn off the sound here. I don't have to do it. And so the idea here is they're trying to figure out if toast lands butter side up or butter side down. And so one of the things that they do, which I think is kind of funny, is first of all, they do this really stupid skit at the beginning where they're all dressed up. And they come up with these different contraptions to find out if toast lands butter side up or butter side down more often. And so one of the things that they do here we go. They come up with a contraption to do this. The funniest thing is anyway, you should watch the video. I question the ways they do their statistics. It's kind of a fun video to watch though. But he gets 7 out of 10 heads and he goes, oh, clearly that's not random, but it could be. And let me just give you another example here. In 1986, Evelyn Marie Adams won the New Jersey lottery for the 2nd time. That's not fair. So the New York Times stated the odds of winning twice were 1 in 17 trillion. And 2 statistics professors said the odds of winning twice is tiny, but it is almost certain that someone would win twice, and they estimated that the probability that someone would win twice was 1/2 over the next 7 years. Sure enough, 2 years later, in 1998, Robert Humphreys won his 2nd jackpot. Now, the interesting thing is, I also have a hidden brain. What are the odds? This is it right here. Okay. I should post this on here. This is a little bit longer than that thing. Maybe I'll post both of these. This is a 25-minute listen, but it talks about winning the lottery. And it says that people who win the lottery are more likely to win the lottery a 2nd or 3rd time. And so it's kind of interesting. And so I guess the myth is humans are really bad at math. And so when you look at something like here, it's actually more likely. The thing is, would you guys like this? You should listen to this. It's 25 minutes long, but it's really interesting. I'm going to add this to my notes here. The thing is, once you win the lottery, then you've got money to burn, right? And so you can you've got more money than the average person, so you can keep playing the lottery. And so that's why you're more likely to win, because you can buy more tickets and you can increase your chances. So another thing that I always like to say here is, if a family has, and I feel bad that I gave away the answer, but you'd probably get it right anyway. If a family has 4 girls in a row, does the quote-unquote law of averages mean the probability of a boy is higher for the 5th child? And hopefully most of you would say no, it's still 1/2, just like it is on all of the other pregnancies. So anyway, let's see, did I cover everything I was supposed to cover? Oh, one thing I forgot to cover, independence. 2 random phenomena are independent if knowing the outcome of one does not change the outcome of the other. So think of it as having no memory. In fact, maybe we'll do one more example here. So let's say that I get head, 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 head in a row. What's the probability of a tail on the fifth one? Janie, what do you think? You're on mute, Janie. We can't hear you.
Sorry, my Wi-Fi cut out, so I didn't hear your question.
Oh, so if I get 4 heads in a row, what's the probability of a tail on the fifth flip?
I don't know, 50% chance, because isn't you're flipping? Or would you do one, shoot, I don't know, you do 1 divided by 4 or 1 divided by 5 to see what you would get? Because you're going to be on your 5th flip.
Okay, you started with the right answer and then you went wrong.
Oh, shoot, that always happens to me.
It was 1/2, just like you said. Don't be talking yourself out of the correct answer, okay? So the idea here is a coin flip is memoryless, okay? And so the coin doesn't care what you did on the first 4 flips. On the 5th flip, it's still going to be 1/2, just like every other flip, okay? Coin has no memory. Now, the question is, let's go to cards, okay? So we're going to test Wes's knowledge of cards, okay? What's the probability that I draw a queen out of a deck of cards?
4 out of 52.
4 out of 52, okay? Now, if I put that if I put that card away, I don't put it back in the deck. What's the probability that I get a second queen?
It would be 3 out of 51.
3 out of 51, okay? So the probability, I forgot to change that. So the probability changes, right? So it's not the same. So in a way, the cards kind of have a memory, right? So the second queen was going to be different than the first queen. It's not like flipping a coin, because you can see that the probability changes. Now, it doesn't change by much. And in fact, if we were to do these, 4 out of 52 and 3 out of 51, so it went from 7.7% to 5.9%, okay? So in this first case, we would call this memoryless, or you would call that independent.
Does your advanced class get into card counting? Just out of curiosity, want to know how many times I need to take this class.
There you go. No, not really. We don't do anything too much harder than this. Has anybody ever seen the movie Rain Man? Have anybody heard of the movie Rain Man?
I have. I'm old enough.
Oh, you're old enough to remember. Okay, give everybody a quick summary of what's Rain Man.
Rain Man is a movie starring Dustin Hoffman and Tom Cruise, where Dustin Hoffman is an autistic little brother of Tom Cruise, or older brother, I believe. Right. And he can instantly count everything he sees within a split second.
Yeah. And so Tom's like, hey, we're going to make money on the card games. So the funniest thing about it is, when it comes to like blackjack and that sort of a thing, they don't use a single deck of cards anymore, because I don't know if Rain Man is a true story, but there are a lot of people that could count cards, and they got really good at blackjack, and they got really, and so now instead of using a single deck of cards, they use like 4 or 5 decks, and then they will only they will split it so that they don't even use, like, they'll take 4 decks and then they'll only use like 2/3 of the deck, so then you still can't count the cards to make it anyway. So so another quick funny story. There was a well, if you guys want to make a really good job, a lot of money, there's a job called an actuary. Okay. And the actuary is really, and maybe I should put that in all caps, really good at probability. And so the idea here is that insurance companies hire actuaries because what's the probability you get in a car accident? What's the probability you die from cancer? What's the probability you cut off a limb? That sort of a thing. And so you have to be really, really good at probability and figuring that stuff out. And so actuaries are the people who figure out how to how much an insurance company should charge for the probability of a given event. So life insurance, auto insurance, health insurance, especially health insurance, because that one's a little bit tougher because there's always new diseases like coronavirus or whatever. So they are really amazing at probability. I've been told there's actually another professor at UVU, and he started to become an actuary. And I've heard that people who are actuaries really enjoy the job, but he didn't think it was all that great. But basically, you have to pass, like, I want to say 6 or 7 tests, and if you pass the first 1 or 2, an insurance company will hire you, and they say to study for the other tests. Now, you have a job to do. It's not just that you can sit there and study all the time, but they will pay you to learn how to do probability. We're just going to do simple probability with cards and, going to a concert and that sort of a thing. And so we're going to do basically simple probability, but you can make a lot of money if you're really good at probability and you can figure out rare events. And insurance companies will pay you to study and learn how to pass all these tests because they're very, very, very valuable. So, but at any end, so I'm sure, Janie, don't you want to become an actuary? Does that sound fun to you?
Did you say Janie?
Yeah, I did.
No, I would not like to become an actuary.
Make a lot of money.
No.
Oh, you'd rather be poor. Okay. That's why you're a poor college student. All right. So anyway, so we'll do these sort of things. But yeah, Wes, to answer your thing about card counting, yeah, it's not good. And in fact, I think it's my next lecture. Well, maybe I should add that into this. Let me see here. It might be the old book. Do we not talk about that anymore? Oh, this is worth talking about. Anyway, I'm going to give you a little thing because I almost wonder if we should do this. But anyway, Las Vegas was built by people who are really bad at math. You guys know Penn and Teller? That's Penn. Penn gives that that quote. There are no casino games or bets where the house does not have a clear advantage. The odds either favor the house or they get a commission. If you're not familiar with the basic information about the games you play or the bets you make, you are just about a guaranteed loser. Casinos owners are in business to make a profit. They did not build all those gorgeous hotels by giving away money. But I will add here that why do you think they give you free alcohol when you go to Las Vegas?
Because I get even better at math.
You get better at math as you keep drinking?
Oh yeah, no, that's exactly why they give it.
Yeah, exactly. So, because they want to keep you at that slot machine or whatever. And yeah, anyway, so they're in business to make money. They love to talk about, oh, look at this person that won our thing. Yeah, they don't. Well, so the other funny thing is about as far as gambling goes, you know, if you go to, especially, what's the old place, the classic Las Vegas? God, I haven't been there for a while. Fremont Street. If you go to Fremont Street in Las Vegas, like that's the old style Las Vegas, and they're like, our slot machines pay back 97% or 95% or whatever. What they've just told you is their profit margin. They make 3% or 5% or whatever on their slot machines, and it's all mathematical. And so one guy who wins $1 million, they don't tell you about the other 999,000 guys who lose almost all the money they make. So they love to talk about the winners because they never talk about the losers. So in state lotteries, the payoff amount is based on after the state takes a cut. And some people say that gambling is a tax on people bad at math or statistics. So, oh, this is one of my favorite headlines. Even though oh, it actually worked. I guess that's a man struck by lightning after buying a lottery ticket. You're more likely to get struck by lightning than you are to win the lottery, but you know, somebody will. So, anyway, yeah, I didn't. It's kind of interesting. So, all right, we'll save the rest of that, but that is kind of interesting. We'll talk about some of the other stuff. I won't go into chapter 15 yet, but I did want to share that with you, especially since Wes made that joke about card counting. All right. We're actually done a little bit. One of the things that I would like to do here. I think I will do this. I've got a little bit of time. And it's easy to do when you're using a computer. So we can do a simulation on an unfair coin simulation. Okay. So let's say that I'm a casino owner and I like to cheat, and I say that the probability of heads, say I make a coin, is 0.4. Yeah, I'm gonna do that. Okay. And let's say that I want to toss a coin. 3 times. I'm going to do this a few times. Now I'm going to do it 10 times. We're going to toss it 10 times. Okay, so I do want, if we're going to toss a coin 10 times, I do want you guys to practice here. Whose turn is it now? It must be Allie's turn. I haven't picked on you very much today, Allie. Can you give me the sample space for the number of heads that I could get? For the number of heads. Toss a coin 10 times. And you're on mute because I can't hear you, Allie.
Sorry, my computer like cut out for a second. What was the question?
Can you give me the sample space for the number of heads if I toss a coin 10 times?
The sample space would be like, wait, what is it? Just like doubled because you're tossing it 10 and there's like 2 options, so 20.
So if I toss a coin 10 times, how many heads could I get?
You can get 10.
You could get 10 heads. What's another option?
You can get 9 heads or 8 all the way down to 0.
Okay, I'm glad you said 0 because people always forget to do that one, but you didn't. So well done. Okay. Now I'm going to do a little bit of cheating here, and I'm going to do. The funniest thing is that you started at 10. Most people start at the other end. That might be why they forget the 0, though. I've never done this way, but I've got this formula here, and I'm going to put this in here. You don't need to know this. But the idea here is I'm going to use an unfair coin, and I just want to make a histogram here. Okay, so this is probability, and these are number of heads. And I'm going to insert, I'm going to make a probability or a histogram here. Oh, I forgot about that. You know, I'm going to start it. Well, I'm going to do it with 10. I've never done it backwards before. I want to see if this works. This is not going to work. Go away, chart. That's supposed to be a 9. Well, it didn't quite work the way I expected. You know, I'm going to sort these. Oh, that's funny. And here, let me fix my chart here so it's a real histogram. Okay. Oh, it didn't include the 10 for some reason. It's close enough. Okay, but here's what I'm going to do. Oh, maybe I shouldn't have used that. Let's go with 30%. Okay, that's a little bit better. Now, if you were to say, would this be normally distributed or would it be skewed? What do you guys think?
Skewed.
Right.
Yeah, you'd probably say it was skewed, right? Skewed right, right? In fact, I'm going to do this again. We're going to use 20% here. And you can see that that one's definitely skewed, right? Skewed, right? Okay, so The idea here, I'm actually leading into chapter 15, which I don't mean to do. I probably should stop here. I want to. The problem is I'm used to going right into chapter 15, but I'm going to stop here. We'll say chapter 15 here. I really should stop. Because I don't want to cover. We're not going to have enough time to cover chapter 15 anyway. So at any rate, we've still got 20 minutes left, I guess. Do you guys have any questions for me? We can kind of treat this as a little bit of a mini review. In fact, if you want, well, we'll see. We could even kind of do a review today again, and then we could have a shorter review on Friday and maybe start at 9:30 instead of 10. Would that interest anybody or whatever?
I personally like the full hour. I was wondering, are you going to post the study guide after today's class so they can start working on that?
Oh, that's a good idea. Yeah.
Okay, because I like doing the study guide because like it tells me exactly the things that are going to be on the test and like which things I should work on.
Okay. Is there anything that you guys want to review now before? I can work on the study guide if we leave early, I guess, but
I personally have to see the study guide and like try and figure out what I know and which things I need to work on, and then we could ask on the hour. But that's just me.
Let me mention this really quickly. Do I have it here? So last time we did 10, 8, 9, 1, and 2. So we're going to cover it 3, 4, 5, and 12 in this chapter. I think I've posted my notes already. So chapter 3 dealt with the normal distribution. Chapter 4 was scatter plots and correlation. 5 was regression, and then chapter 12 is the one that I'll post today. That's going to be dealing with probability. Is there anything you guys want to review, or do you want me to get started right away on the study guide, and we can get out of class a little bit early today?
That sounds good to me.
Easton, what do you think?
I'm good with either one. Doesn't matter to me. If we get out of class early, I'm just going to go start on the homework.
Okay. Anybody else have any strong opinions? Yami never showed up today. I wonder where she was. All right, well, tell you what, I will get started on the study guide. I'll let you guys get started on the homework. We'll do our review on Friday and the test on Friday. And I need to write the test too, so I guess we'll get out a little bit early, and then you guys can get started on the other stuff early, so that I don't go into chapter 15. But I will tell you this, chapter 15 piggybacks on chapter 12 a lot. So, alrighty then. Well, I will let you guys go. Is there a question?
How many chapters are we covering for this exam?
So 3, 4, 5, and 12. So that's 4 chapters.
Okay. All right. Thank you.
Okay. Anything else? Alrighty then. Well, I will let you guys go, and we will talk to you later.
Okay. Thanks.
Mm-hmm.